It is part 2 of section 5.2. In the first part, we considered the Euler method, which is the first-order Taylor method. Here in this part, we'll study higher-order Taylor methods. They are based on Taylor series expansion. If we expand the solution y of x in terms of mth order Taylor polynomial about xn and evaluate it at xn plus 1, we can get here this equation. Y at xn plus 1 is here Taylor expansion evaluated at xn, and this is the remainder. In our approximation, this portion will be ignored. Now, we will use for the derivatives here, for example, y prime xn is same as f of x and y, and y double prime is now, by differentiating this f, we can get this one. So that in general, y kth derivative is same as f k minus first derivative with respect to x of f. Okay, so here, this equation can be rewritten in this form. So y at xn plus 1 is now y at xn plus here that term involving f and f derivatives. The Taylor method of order m is formulated in this way. Now, this portion has h term at least once. Here h squared, and last term will be h to the m. We factor out h, and the remainder part is called t sub m. Here, t sub m is given in this way. So after truncating this portion, we just get this portion to get the nth order Taylor method. Okay, that's the higher order Taylor method. Okay, here we have a remark. Once m is 1, then it becomes the Euler method. Once m is 2, for example, then we can formulate in this way. That is T2. As m increases, the method achieves higher order accuracy. In fact, globally, mth order accuracy. However, it requires to compute derivatives of f. Okay, let's see this example. Consider the initial value problem, the same problem we considered in the first part for the Euler method. Now, we'll try to find the t sub 3, so that try to get third order Taylor method and perform 2 iterations to get y sub 2 with h is half, so that y sub 2 is an approximation of y at 1. Okay, here for part A, we have y prime is given in this way, so that here f prime derivative is y prime and 3 minus 3x squared plus 1, and y prime is again these terms, so that we replace y prime, so that now simplify here. For y double prime, here we differentiate these terms, and we can get that, and y prime is again this one, and then replace y prime with that, and here simplify, so that T3 which is the combination of these three terms, and we use this term, that one, and we recheck this. And once you try to get higher order Taylor method, then this computation of the derivatives of f is quite complicated. Now we are dealing with a very simple slope f. However, sometimes f prime and f double prime is really complicated. Okay. For m large, the computation of Tm is time consuming and cumbersome. Okay, here for part B of the problem, here we need to two steps along with h is 1/2 to get y sub 2. Okay, T3 is defined and h is half and beginning point is 0, and here the initial value is half. And y sub 1 is same as y0 plus h times evaluation of T3 at x0 and y0. We get that one. There's y1. y2 is now y1 plus h times evaluation of T3 at x1 and y1. So we can get that one here. Now its numeric value is given in this way, and exact solution so that we can measure the difference, and we can see here now is 0.03. You can see that this third order approximation is much better than first order Euler method. Okay, that's the end of the section. Thank you.